on the board. So, and all those numbers you see, in fact, notice this is the so, this is a capillary. Some isolated capillary is considered here, and what is considered some virtual central part by this dotted line, and the left side, which is closer to the heart, will term it arterial and venous. And that's why it is given here arterial and venous. And you can see the different constituents of blood given here using symbols, but the aim of the topic here is to explain what are the driving for water molecule across the capillary and maintain the balance. So for that reason, let me switch on the board. Of course, let us clear everything. And let us consider a single capillary. Central part and the arterial end. Arterial part and venous part, and we have to discuss what are the pressures being experienced there. So to understand this, I suggest you to focus on a question, a problem, to use some numbers for being able to understand that. So let us initially read the first problem given here. So assume that the osmotic pressure of the blood is 7 atmospheres and that it has an excess of 22 millimeters of mercury osmotic pressure compared to the interstitial fluid. And what is asked here, express both osmotic pressures in millimeters of mercury. So 7 atmospheres is blood osmotic pressure. Let me write. P blood osmotic is 7 atmospheres. Since other values are given in millimeters of mercury, we need to transform this in millimeters of mercury. One physical atmosphere is 760 millimeters of mercury. This I wrote, I think, previous time, which means that we need to multiply this by 760, and so let me use the calculator for quick calculation. We've got 7 multiplied by 760, so we've got 5,320. So this is the osmotic pressure of blood, but we've got here, this is capillary wall. So this serves as a membrane through which water molecules pass. So in this case, we've got another solution that in the interstitial space, which has got less osmotic pressure, and this is given in the problem. So see here, blood osmotic pressure is by 22 millimeters of mercury bigger than that of interstitial fluid. So thus we can write that osmotic pressure of the interstitial fluid is this minus 22. This we can write directly. It is 5,200. So 98 maybe. So let me quickly use this minus 22 to check. Yes, absolutely correct. Millimeters of mercury. So thus, both solutions of interstitial fluid and that of blood have osmotic pressures. That's why we need to talk about the so-called net osmotic pressure, which is the difference between them. So this by this we have calculated 22 millimeters of mercury. So, and it is directed in what way? Since interstitial fluid is less concentrated, we know that net osmotic pressure has got direction from less toward high, and the content of blood is homeostatic parameter. It is kept within limits. So thus we've got one and the same value of 22 millimeters of mercury. I'm just write 22, no space to write the unit for the osmotic pressure. What other pressure is exerted on the capillary wall? This is the pressure due to the functioning of the heart, so which we term hydrostatic, considering the heart being as our central point. In case of gravitational potential energy, we consider the surface of the earth, or earth as a thing, as an object according to which we measure location. So that's why in this case we talk about a kind of hydrostatic pressure considering heart, the reference location or position. And in the next problem, which is about the albumin loss, those values of hydrostatic pressures are given. 35 millimeters in the upper end, in the arterial end, and 15 millimeters in the venous end. And that hydrostatic pressure is directed upward because as blood flows through the vessels, it tends to expand them, so to apply pressure outwardly. So for that reason, in our picture, we'll write hydrostatic pressure bigger, so not enough space, but this must be bigger than this since it is 35. And this part is less because it is 15, as given in the problem. So let me proceed. So we've got here just to repair the picture. So to complete the Venus end and to represent hydrostatic pressure in the Venus end, which is 15. So please don't forget to make this longer. I cannot extend here. So thus we've got upward pressure in the venous part, which is 35 millimeters, and osmotic pressure 22 millimeters, which means that what is net pressure in the arterial part, P arterial, what is it? The difference between them, 35 minus 22, which is 13. And what is, and it is that net pressure, let me use some other color, P in the arterial end, but net pressure being 30 is directed outwardly. Why? Because it has got the direction of bigger pressure, that of hydrostatic pressure. What about what is the situation in the venous part? So we've got net pressure P venous, which is what, 7 millimeters. So let me not write the unit, 7 millimeters. So thus we've got 7 millimeters inwardly directed, 13 millimeters outwardly directed. So thus water leaves the capillary in the arterial end due to that P arterial net pressure and enters in the venous through the venous part due to the net pressure of 7 millimeters in that part. So there is a slight non-equilibrium. So let's see all those numbers. Let you see all those numbers in the picture, which we have. So in the picture, everything which we have done is here. We got 35 millimeters. What is this? Hydrostatic pressure in the arterial part. In the venous part, it is less due to the bigger distance from the heart. Location is away from the heart, that's why the value is less, 50. So we've got same osmotic net pressure which we have calculated of 22. So thus the net outward pressure, outward, why? Because those two vectors being subtracted, the result would be vector having direction of bigger one. So thus 13 millimeters is what? The net pressure net between hydrostatic and net osmotic exerted in that part of the vessel. And the net pressure inwardly directed of 7 millimeters in valve, which really is easily compensated by the lymphatic relation. That equilibrium, although not exact, is termed Stalin equilibrium for capillary exchange. So this is Stalin equilibrium for the water exchange between blood and the interstitial space. And as I told you, that small difference is compensated via lymphatic circulation. So thus, some applications of this, which we can discuss on the basis of the same example. That problem you can find in the red book. So now let us read the whole problem. Suppose there is an albumin loss from the blood that dropped the blood osmotic pressure from this value, normal one, 50, 53, 13. And everything else, let us consider same. What would be the result of this albumin loss? Change in blood osmotic pressure by 7, reduction by 7 millimeters of mercury. So let us see my picture, not so nice as in the presentation, but useful, I hope. So thus, blood osmotic pressure, instead of 22, is reduced by 7 millimeters. This is net. Let me see. This one, blood is reduced by 7 millimeters, which means that P net would be of new value as the albumin loss. It will be 15 millimeters of mercury. So thus, instead of 22, as a result of albumin loss, we've got 15 everywhere. And what would happen then? We will have osmotic net outward pressure, not of 13, but of what? We've got of 20, bigger. We've got net venous pressure 0. So thus, this is in case of albumin loss, which means that we've got very big outflow of water from the capillaries and no inflow. There's nothing which enters the capillary, which will result in edema. Edema being an indicator of some blood loss, being a kind of disturbance, sometimes serious. So all those things are discussed without numbers, but I think that numbers are useful to understand the phenomena. Again, not working. I'm waiting the presentation to be switched. In the text, it's given just edema. Edema, and we even show the why it occurs. So, and then finally, not working. So, in the next slide, circulation is discussed. initially general, but you must have discussed this in the topics, in the risk of exercise extension. I hope that in your class, and you must be very well acquainted with it. So that's why I'm going directly to focus, assuming that all those things you know even better, and to focus on the role of self-understanding in investigation. So, and here I would like to explain things which students consider difficult, but it's not. In fact, what makes a view light stable? Stable. So, not to collapse, not to burst, but to stay the same size. This means stable. And that, for that purpose, let us always, we are doing this. I'm waiting for you. So always we consider what pressures are exerted. Let us consider the shape of alveoli spherical. Of course, this is approximation, but for the sake of discussing the phenomena, let us consider spherical alveolus, a single one. I'm going to clear this, and then to draw a single alveolus. So we've got here an alveolus. Inside, we've got air, which means that pressure here is exactly, let us consider it very close to the atmospheric pressure. So that's why I may write it P atmospheric, which is exerted outwardly. So it tends to expand the alveolus. And also, we've got, since the membrane is spherical, we've got forces due to surface tension which are tangential, which means that they do not cancel each other, and they determine net inward pressure, which is called pressure due to tension, PT. So thus, alveolus will be stable if, so let me write, P atmospheric equals P tension. If atmospheric pressure is bigger, then we've got expansion. It will expand. If P atmospheric is less than, then it will what? It will reduce in size. It will shrink all reduction, expansion, reduction, reduce in size. Oh. Expand, it will expand, it will reduce in size. So, we know what is the relationship between tension and membrane tension, and we studied this previous lecture. For spherical membrane, we've got tension being pressure, I'm going to write here PT, being pressure related to it, radius divided by 2. From here, we can express That pressure being twice T divided by R, for the sake of discussion. So, let us now see the text. Suppose the membrane tension is increased. What would happen? What would happen? Let us see my picture. If, to take some color, suppose the membrane tension is increased, the indirect proportionality. That inward pressure will increase. It will become bigger than the outward pressure, which means that it will collapse, reduce in size, as given in the text. It will collapse. Okay, in the next slide. If the radius decreases, by some reason, the radius decreases, this indication, suppose this decreases. It is in the denominator, this will increase, it is inwardly directed, it will collapse. So, next, if the bubble begins to expand because its membrane strength is insufficient to stabilize it at that radius, it will continue to expand until rupture. Let us see now in the formula. Suppose it begins to expand, which means that the radius increases, which means that the inward pressure decreases, tension decreases, which means that it will continue to expand because of this condition until rupture. In what way this is prevented? In what way did the body controls the size of alveoli to prevent collapse or rupture? So, using surfactant. Surfactant is the fluid, is a fluid coating the alveoli, which reduces tension. So thus, let me just draw this here, suppose, and this is some section of the alveoli, and we've got here surfactant. And if the radius decreases, surfactant becomes more concentrated. It reduces tension. If it is concentrated, then the tension will decrease. So see here, radius decreases, also tension decreases. So we've got both things decrease, the ratio stays same. Alveolus is stable. If it expands, suppose radius increases, it becomes more diluted, the surfactant, because it will be distributed over bigger surface. That's why concentration will decrease, its concentration, and tension will increase. So thus, if radius is increased, tension also increases and the pressure stays same, and the alveolus stays same. So this is not difficult. Just using single equation and a little bit thinking. So just to see next topic, internal energy, heat and temperature.
the internal energy important concept. We will study the difference between heat, internal energy, and work, which is the foundation to understand the biophysical thermodynamics, which is the first part of the next semester. That's all for today. Today, I would like to ask to stay here groups, number 1, 4, and 5. Yeah, other groups, please.